to introduce Dr. Gil Hanson, who is Emeritus Distinguished Service Professor at Stony Brook University. I hear he just retired. He received his PhD in geology from the University of Minnesota. His main research has been in using isotopes and trace elements in rocks to determine the sources and histories of rocks. In the mid-90s, he became interested in the geology and hydrology of Long Island. Much of the research on geology of Long Island that he has advised has been undertaken by pre-service and in-service science teachers. So with that, I will open it up to Dr. Hanson.
Very nice to be here. You might ask, why would I have earth science teachers doing the research? And I've been the earth science education advisor now for over 20 years. Not anymore, I stopped as of January 2nd. But my whole philosophy behind it was, would you hire an earth science or a music teacher that didn't sing, didn't play an instrument, but taken a lot of courses and has been to a number of concerts? And what would your reaction be? Probably not. But we hire science teachers who don't have the basic workings of science, which is research. And we now require that all earth science teachers that go through, or students that go through the program, must take at least one research project where they collect their data, or at least go through the data and figure out what the problems are and write a report and give an oral report on it. And I think that works out quite well. Now, I just thought I'd better say that because you might wonder why earth science teachers. So. And this is going to be an interesting process for me because this is the first time I've given a geology talk on Zoom, unlike the other teachers who are now been teaching at the university. They've all been have had lots of progress with I gotta find, here we go. Lots of experience with Zoom. So thank you for being guinea pigs with me. This is a digital elevation model of this middle of Long Island. And the digital elevation model gives a completely new sort of look at the topography and geomorphology of any site. And the digital elevation model was sort of established in the 1990s. And what they do is they take, at that time they took a topographic map, and in this case they went every 10 meters on the topographic map and made and took down the elevation, the latitude, and the longitude every 10 meters on the map. So they had a huge matrix. They then took that matrix and put it in a program so that you can determine, put it in a program so you could see all the points in a matrix, assign different points based on their elevation a color. And so you can see here, blue is going to be the lowest elevation and red is the highest elevation. And not only that, they introduced shaded relief. And when you add the shaded relief, that means then that the features stand out. And if you look carefully at this, you'll see where the shadows are. In this case, you can see a lot of shadows on that side. You can see a little bit of shadow here, no shadow there. So the sun is actually shining from the northeast, 45 degrees northeast and 45 degrees up in the. And when you do this, you can just see features that are just not easily seen on a topographic map. And so now this is Long Island, where we live right now. Stony Brook is right there. And we would be sitting right there if we were at the university, but we're not. So we got a number of features that really stand out here. And here's the three village Port Jefferson area. This is Port Jefferson, that's Port Jeff Harbor. Port Jeff Village is in here. And then this is the whole of the Setauket, Stony Brook area. And you can see there are a lot of features on there. And a lot of people say there's no geology on Long Island, but just looking at these features, you see there are lots of features. Is that right? And it's quite clear that these features are telling you a lot about the history and the geology. So let's just talk introduce some of these features very slowly. Here's the Ronkonkoma Moraine. You've heard of it. And you can see it's not a pile of sediment that just continuously goes across here. It's got little bumps on here. And it's made up of a whole bunch of little bumps. And these bumps are called push moraines. And where there is no push moraine right through here, you have what we'll call hummocky terrain. And we won't talk a lot about that for the rest of the island. But you can see it's complicated. It's not just a case of the glacier came down, deposited, and then went back. Then up here we have the Harbor Hill Moraine. It's been given different names by different people, but this is the Harbor Hill Moraine going across like this. And this area here is been named the Stony Brook Moraine, which is kind of nice to have your own submarine in your area. And we're sitting in here, so you can see there's a real definite feature. And then this is the outwash plain for the Ronkonkoma Moraine. This is the Harbor Hill Moraine. This is the outwash plain for the Harbor Hill Moraine. And so this is the high areas, and these are the sediments that were flowing out from the glacier to form these plains. So that's a pre-description. And I'll tell you what I'm going to talk about. Excuse me. In this presentation, I will describe how glaciers form, advance, and retreat. I was asked to try to make things simple, and I'm going to try to not make bad feelings toward you. That I think you need simple, but sometimes just a simple description works. But in any science, jargon comes in, and it makes it very difficult. So how glaciers form, advance, and retreat, the features associated with the Stony Brook Moraine, Harbor Hill, how the tunnel valleys in 3B and PJ form. The odds are you probably haven't heard of tunnel valleys, but the odds are you've been driving through them all the time you lived on Long Island. And one of the things I like to hear afterwards is that people will tell me, I live in a tunnel valley, or I have to drive in a tunnel valley to get to work. And how the climate changed from 20,000 to 11,500 years ago. So after each of these topics, I will take questions and comments on these topics. So how do we make glaciers? Well, they're made out of snow. And how does that work? Well, a snowflake falls. There it is, nice, beautiful, hexagonal, six-sided feature. And then 2 days, it disintegrates pretty much. And then after 1 year, you can see that it's now a bunch of little crystals. And then after 2 years, these crystals are starting to accumulate, and it fits tighter. If you ever notice a pack of snow, even in your yard, if it hasn't been warm, it'll collapse just on its own. And some of it's due to sublimation, but some of it's just due to the recrystallization of the crystals. Firn then is after 2 years, and firn has also been has a a foot or two or three of snow on top of it, and then after 5 years it becomes ice, and so you actually get ice. Then after 10 years the crystals get larger, and they are all interconnected then. So the snow from the previous winter does not completely melt in the summer. The pile of snow gets deeper. And this is what's critical for making a glacier. It's got to be cool enough this summer that all of the snow from the previous year does not melt. And the coolness of the winter doesn't play much of a role. In fact, if it's really cold, you aren't going to get much snow. And then ice crystals grow, changing from snow to firn to ice. And then when the pile of ice is 100 feet thick, it begins to flow. So the ice can actually flow. And we know that, you all know that, because glaciers flow. And so once it gets to be 100 feet thick, it begins to flow. And cool summers are more important than cold winters in producing a glacier. So there are glacial and interglacial periods. Glacial periods last about 100,000 years. Interglacial periods last about 10,000 years. We're in an interglacial period. We entered this interglacial period 11,500 years ago. Ask yourself, what does that suggest? During glacial periods, glaciers systematically advance and retreat. The glaciers just don't come straight down for 50,000 years and then go back for 50,000 years. They go back and forth during that period of time over long distances. And then the front of the glacier advances when the snow accumulation exceeds melting. And that's key. The glacier always flows in one direction. And when we say the glacier retreats, it's only the front of the glacier that retreats. And so the front of the glacier advances when you get more snow accumulation, and it exceeds the melting. And then the front of the glacier retreats when melting exceeds snow accumulation. And so this is the last interglacial to our present interglacial period. And then this is the glacial period in here. And this is the average global temperature, and that's in degrees centigrade. So here it's around 16 degrees. And then you can see it gets cold as around 11 or 12. And here you can see now we have a period starting at about 125,000 years ago. It starts getting cold, warms up, gets cold, warms up, gets really cold, warms up, gets cold, warms up, and then really, really cold just before the warming period. That happens pretty much every time. And in the northern continents, this period, the periodicity means that we've got periods like this about 20 times. So about 20 times this is happening, going back and forth. And we are quite sure that this is going to continue many millions of years into the future as well. So this is not as if there's one glacial period. We've had it, and now we're in an interglacial period, and we're going to stay here forever. In fact, we should be going into the interglacial period right now. But there's a suggestion now, because of the global warming, that this may prevent us from going into the next glacial period right now. So if you like glaciers, and they like them having them come down to us, well, you're going to have to wait longer. Now, I want to show two videos. I hope it works. Like I said, we're trying new things here. Unshare, and then share. I didn't intend for that to be there. Okay, can you see that? Can everybody see it? Okay, so this just shows the rate. Let me just start from the beginning. It goes so really fast, so I have to be careful. So it starts 120,000 years ago. We're just coming out of the last interglacial period. And you can see now the glaciers start forming. They come down. And then around 105,000 years ago, they back up, almost disappear. Then they come back down and way far out. The blue are lakes. They're lakes in front of the glacier. So you can see that the glaciers are coming and going back and forth. At around 60,000 years, you're going to see it's going to be very close to Long Island right here. It doesn't quite make it. Look at that. Oh, just barely. And now it goes back. And now the one that's critical for our talking today is what happened about 30,000 years ago. And 30,000 years ago, it's going to start around up here. It's coming down. And then here's Long Island. See if it reaches it at 20,000, somewhere in there. Yep, there it comes. And then it goes back up and slowly retreats. And then now you're going to see everything sort of disappears. And by 5,000 years ago, no more ice on the North American continent, on the flat parts. Okay, let's go back to where we were. If people are interested, I can show the other video. This is taking more time than I thought. And so glaciers are dynamic, as you can imagine. They're hard, and so they and they're rather dense. They flow away from the area of thickest accumulation. Some people think glaciers always flow south. No, they just flow away from the area of thickest accumulation. We're talking now mostly about large continental glaciers, which are called ice sheets. They actively erode, transport, and deposit rock and sediment. And here is just a picture then. Here is the zone of accumulation of a glacier. The glacier then it's a higher elevation here, just due to the piling. And so therefore the gravity is going to just force it to travel in this direction. And then as it gets to the front, it travels to where it starts to melt. And then if it, at the furthest extent, they call this a terminal moraine. That means that's as far as the glacier got. And so you can see that it's not going to go any further because it's melting too fast. So front advances or retreats depending on whether the rate of melting is slower or faster than the rate of flow of the glacier. And here's a picture then of a glacier. This is an alpine glacier or valley glacier. So you can see the glacier here. And then this is the front of the glacier. And then the glacier meltwater, it's coming off of here. And you can see the glacier meltwater is usually coming from under the glacier. It's coming from tunnels under the glacier. And the water's coming out and it's carrying lots of sediment. So it transports silt, sand, and gravel away from the front of the glacier into braided streams. And the streams deposit then layers of sand and gravel in an outwash plain. And you get this very beautiful pattern. It's called a braided stream pattern. So this is the outwash plain from this glacier. And here's another sort of view of what it looks like. So you get a view of the what's underlying it. Here now is the glacier. This is then the outwash plain. You can see the braided streams. You can see now that here's a tunnel with water in it streaming up through here. It's forming, feeding. Here you can see that was a tunnel, that's a tunnel, that's a tunnel, that's a tunnel. Pretty much all the water is coming from the tunnels. And we'll talk about that a little bit more later. And then you can see these are the chunks of ice that have been buried by the sediments coming off the glacier. And you can see once the glacier is gone, these become kettle holes. We'll talk a bit more later about kettle holes. And the other thing is that the terminus of glacier does not always have to have a moraine. It doesn't have to have a moraine. It depends on how long it was sitting there. Okay, and then another feature I want to discuss is till. And here's the ice traveling. And then the till is at the bottom of the ice sheet, at the bottom of the glacier. And generally, if you're on a flat area, not too many bumps in it, the thickness of the till is about 1 meter or 3 feet. Rather universally, it's got a common thickness. And the till is that material at the base of the glacier consisting of boulders, cobbles, pebbles, sand, and silt. It's picked up by the glacier traveling across the material below. As it's traveling, it's also abrading and crushing those particles and making them smaller and smaller as they travel. And it's leaving, since it stays at the same thickness all the time, you know it's also leaving a lot of material behind. And at the very front of the glacier, as the glacier is advancing, the flow is advancing, you're going to see that the ice is going to get too thin to flow anymore. And what happens then is that the ice that's behind it starts pushing up, and up, and the till that's at the base of the glacier gets carried onto the surface of the glacier. So you get piles of sediment sitting up here on top of this ice. This is active ice, and this is dead ice. And so you can see it just starts packing up here. And as this melts, then this becomes the dead ice also. And so you get this fairly large stagnant ice area. And it makes very interesting features. This is a hummocky moraine, which is what they call this kind of a moraine. You can see this is where the stagnant ice was, and it was just dumping. It just dumped the material that was on the top. And it forms then piles, thick piles where the sediments were thicker on the glacier, and then thinner ones where there wasn't much sediment on top. So you get this beautiful, depending on how you like things, but for me it's a beautiful sort of pattern right here. And so you can see this is also called knob and kettle terrain. So you can see you've got knobs, and in here you probably have a kettle. So how do you make a kettle? And almost everybody has this wrong. The model that people think of as that a kettle is formed by a piece of ice sitting on the top and then making a depression just by its weight pushing it down. No, a kettle is made by ice that's been buried. And then when the ice melts, you get a kettle. Now, do you always have water in a kettle? Do you have all kettles have ponds? And most people think they do because they say, oh, the reason there's a pond there is that the ice, when it melted, leaves the water behind, and the water in the kettle makes a pond. And that's not true. For a while that may be true, but it's not true for the main part. So how to make a kettle pond? Well, if the groundwater table level is below the bottom of the pond, it's going to be below the bottom of the kettle, it's going to be empty. And almost all kettles on Long Island are empty. I don't know how many there are on Long Island, but just on campus, I've had the people count them. And even in a small area, we find 10 or 20 kettles just on campus. Depends on how small a feature you want to call a kettle. And they're all empty. And so then as the groundwater rises, it's not a very good diagram, but that's just the water level in the kettle. You can then see that it goes up, and as you raise it, you get higher. And so this is what a kettle pond now, where the groundwater table is intersecting into the pond. So this is time for questions and comments. Are there any questions or comments?
Okay, I don't see any questions in the chat box. Does anyone have any questions? Laurel, she didn't put it in the chat, but she's raising her hand. So I'm going to unmute you, Laurel. Or you have to unmute yourself, actually. Laurel, you have to unmute yourself.
Okay. I did raise my blue hand.
I see it.
You saw that? Okay. I wanted to ask, if it weren't for the global warming, would we be heading into a period of glaciation?
Right now, the last interglacial started 11,500 years ago. The amount of sunlight that's hitting us right now, where it's important to determine whether you're going to get glaciation or not, is at its low ebb, and the odds are that we should be going into a glaciation period right now. But instead of getting cold, okay.
Go ahead.
So yeah, we should be going into a glacial period. Does that answer your question?
She's muted. Laurel,
Yeah, I got a phone call, so I had to mute. But anyway, hold on, Brigitte.
okay. So Laurel, we'll get back to you in a minute, okay? I have another question in here, Dr. Hanson. How are global temperatures from thousands of years ago determined?
They can determine it by a feature called oxygen isotopes, and the oxygen isotope ratios in different kinds of substances are based on the temperature. And they can use also other things like, this sounds weird, beetles are a good one. Go around and find out what kind of beetles you have, what kinds of trees, this kind of thing. There are actually a large number of ways you can actually do it by just looking and comparing to present time.
There's another question here. Do the tunnels form rivers?
They have streams in them, yes. We're going to talk a lot about that. I'll come back to that in detail.
Okay, I think that's all the questions right now.
Okay, thank you.
Thank you.
So here's the campus. I think you all recognize it. Here's Marburger Drive. Here's the health sciences. Here's the hospital. And here is the Stony Brook Moraine. And you'll notice here, this is all pushed up. So this is a small pushing. The glacier, when it reached this point, was pushing this material up and forming this ridge. And then it came across the top of here, and it actually, at some point, stopped about right here. And then you're going to see, you see these features in here? I hope you have a good enough view of it. These are stagnant ice features. This is a hummocky terrain. You get these funny ridges, lots of kettles. See all the kettles in here? Kettle, kettle, kettle. And you may say, why do kettles often have different shapes? Well, it depends on the shape of the ice that was left in there. And so these are here, and you can actually see here some more. Here are some more of this stagnant ice. And this is the outwash plain. You can see here's a place where sediment is being brought down through the streams in the front of the glacier. So let's just see what happens. So this is the outwash sand and gravel. There's a stagnant ice regime here. And then here's an active ice. And so we can go back then again. This is the outwash plain. And so you can see now the outwash plain, whoops, goes up to, it might go further up in here. This is a bit tricky deciding because this development has sort of ruined it. And then this is the stagnant, yeah, that's why I put the stagnant ice up in here. And then the glacier itself was sitting, active glacier was sitting there. Now, whenever I'm going up toward the university from the south, traveling along here, I sort of get a tingling. because you can see this is the outwash, the end of the outwash plain. You can see it's got a really low gradient as you go up this way. Now you're going up this hill. You're seeing you're going up onto the stagnant ice. You probably have a hard time driving up to it, but I'd like to think about driving up onto the glacier if you're there during the glacial period. So that's kind of interesting, I think, is to think when you're going around Long Island, just think of what it was like before. So let's just look at some of the features on Long Island. This is on campus. This is what the material looks like in an outwash plain. This is a section on campus where they cleared this off. And so you can see you got a lot of different kinds of sediments. The close-up shows you get sands and gravels. The sands usually would be bars in the stream, and the gravels are going to be the bases of the stream where the sand has been removed and only the gravel can be left behind. So you get then this continuous, in the braided stream, the streams are going back and forth all the time. And so you go, at any one place you'll have a bar, gets wiped away, puts in a gravel, maybe a little bar, gravel, and so forth. I got it. And then you can see it just keeps repeating itself. Sand, gravel, sand, gravel, sand, gravel. And then lots of, in this case, cobbles. I think there might be some, yeah, there's some boulders, there's some cobbles. It's just loaded with all sorts of material. So this is the till, and this is the outwash sediments that are affecting it. Okay. So an end moraine, ridges of unsorted sediment on the ground. I've got to do something. It's asking me to do something here. Oh, I see. It's okay. Am I still in share? Yeah, I am. Okay. And they're made of till. And if it's just been dumped, it's made of till. If they and they make small piles, not big piles. If they are made of sands and gravels and other sediments, if they're formed by a glacier pushing sediment forward into piles like a bulldozer. And that's what's happening on Long Island. The glacier, when it came down, we had all the sediment. As the glacier came down, rather than going over the top of most of it, it actually just pushed it like a bulldozer in front of it. And in this case, you can get moraines that are hundreds of feet tall, 100, 200 feet tall, 300 feet in on Long Island. And these are small, usually 10, 20, 30 feet. These are really tall, it can be hundreds of feet. Can you see what I'm seeing?
Yes. But we don't see it in full screen. Now we do.
Yeah, I went off, I forgot to come back. And so this is a push moraine. And you can see now that this is a scale. This is 5 kilometers. That's 3 miles. And the glacier now, when it hits these soft sediments, can actually just push them. It digs a hole back here. And as it digs that hole, it pushes the sediments out in front of it. Now, since the sediments are piled on top of each other, they don't make just a simple pile. They actually move out in sheets. You can see these sheets are up to 5 miles in length in this case. And you also see that these are on the order of many tens of feet thick. And that's what's happening on Long Island. Our moraines are made this way. You get this thrusting, called thrusting, and then you get these trenches that are behind it. And we'll be talking a bit about this. And here you can see water's coming out of a tunnel and depositing out onto the outwash plain. In this case, this is called a fan. You can see it make, in a lake, you'd call this a delta, but on the land surface, that's called a fan. So the fan is forming out in front. And then if you have a whole series of these lobes that are coming down, you're going to see some of them are going to be pushing the sediments. Some won't. Some won't push the sediments. So you may find that you'll have lobes in some places and no lobes in other places. In this case, you'll get just stagnant ice there. And here you'll get beautiful moraines. So pretty much what we've been talking about. And then here then is the Stony Brook moraine. And you can see that was pushed by one lobe here. Then here is another lobe that didn't really create much of a moraine. And in place, someplace, yeah. And so this is a continuation of Harbor Hill Moraine, but it's also made up mostly of hummocky terrain here. And then since this is one lobe and this is another lobe, you're going to see if you go live on Belterre in Belterre in Port Jefferson area, this is an interlobate moraine. It's a moraine that formed between this lobe and this lobe. So we got this interlobate moraine. Then in between here, you can, right at the edge here, we can see we have a tunnel valley coming up like that. And then right in front of it, just like I talked about, we have this outwash fan, huge outwash fan. And what's being proposed is that this area was covered by ice. The water was traveling up through here and then carried all the sediment. You're also going to see we have lots of tunnels off and through here. These are all tunnel valleys. And we'll go on to look at this, shows them right offshore of Long Island. Here's the Sound. Here's the Three Village area. Right off Sound, we have this huge trench. It's up to 800 feet thick, or under 800 feet below sea level. Here it's 700. There are other places it goes as deep as 800. So that's below sea level, this trench is. Right now, it's not a trench in the Sound because it's been filled with glacial sediments and with the later sediments. So you can see we have a trench associated with it as well. Now, one of the questions you might ask is how do you get unconsolidated sediments being pushed up in sheets? And Van Davis really likes to do modeling. He's very good at thinking about how to make models. He came up with the idea of using flour and colored chalk to model tectonics. In his case, it was tectonics, but it applies beautifully to glacial tectonics. And you have to admit, flour is unconsolidated. So here he is, he's put the coloring on, now he's putting on flour. And then afterwards, you cut it. And what do you see? You see these same features we saw before. You get these thrust sheets. They're thrust sheets. You actually get nose folds, thrust sheets, thrust sheets, thrust sheets. You get the same sort of features that we see in the glacial tectonics on Long Island. We've done enough research to see this is repeated over and over again. So, questions or comments on how we make glacial tectonics and how we make the moraines on Long Island?
Okay, so here's one question. What of the little ice age and the fluctuations of warming and cold periods? Do these correspond to the advance and retreat melting of the glaciers?
Yes, during the Little Ice Age, there was some advancing in some areas. Some people think that the Little Ice Age was the beginning of the next glacial period. They say that if we didn't have this global warming, evidence suggests that we would be now slipping into the glacial period. But because of global warming, we're not. And that's hypothetical, but it's something worth thinking about. But the Little Ice Age was only a few, not very much colder at all, but it was colder. It was getting colder. Actually, went about 4,000 years ago, up to 4,000 years ago, from 8,000 to 4,000, we were much warmer than we are now. So even since then, we've been cooling.
C. Barnes, I asked you to unmute. Did that answer your question? I don't know if they're muted, so okay. Another question. How thick was the glacier over Long Island?
Say that again?
How thick was the glacier over Long Island?
Well, at the very front, it would be negligible. And then probably if it went to the furthest extents of the island, it could have been thousands of feet thick around here.
Okay. Let's see if there's another one. How do glacial tectonics relate to plate tectonics?
They're very similar. That's why Dan Davis got interested. He was an expert on tectonics and figuring out how plate tectonic sheets move and what causes them to do this thrusting on top of each other. And he came up with the model actually of a bulldozer pushing. And I went to one conference where they were talking about that. We just need more people to look into this model a little bit more. And they used his modeling of tectonics for that. So it's not exactly the same, but you can picture it. The glacier is a sheet, tectonic sheet, and the material underneath it is another sheet, or plate if you prefer.
Okay, that's the end of the questions. Anyone else, if you want to raise your hand on virtual hand or type it into the chat? If not, we're going to move on. I think that's it.
Okay. Subglacial streams and tunnels forming tunnel valleys. Every summer on a glacier, like in Greenland, there is just an incredible amount of melting because the sunlight comes out, and then in Greenland especially, it's going to be having the sun shining it on large periods of the day. There's just an incredible amount of melting, and all that water has to go somewhere. And as it travels, and then I'm going to show, it isn't just Greenland. This is a picture of Antarctica. And they've lifted up the glacier. This is the glacier. They picked it up and said, let's look underneath it. And they actually can use, I think it's used radar to look at the bottom here. And they can see that underneath there are all these streams that are flowing under the glacier. And these are lakes. These blue dots are lakes. So there are lots of lakes under the glacier, and there's also a lot of streams. So because the glacier is so thick, it's actually melting at the very bottom of the glacier, just from heat within the earth called geothermal heat that's coming up and melting it. So this is not an unusual feature. And a big glacier, like we had in North America, will also have had a lot of these streams, and these streams would be coming, and then they have to exit somewhere. So how does it work? Here's the glacier, and here's the top of the glacier. In this case, it's got a lot of sediments. Doesn't necessarily have to have any. And then here is what's called a moulin. It's a French word for mill. And then you can see now the water is coming into these moulins, and then as it does, it fills the moulin up to a certain point. And then if that's the case, this is going to tell you what the hydraulic head is going to be. And if we got hundreds of thousands of feet, that can be a huge hydraulic head. Is that right? And then I usually have a model that I bring to show this. And I was wondering how I can't get into the university. They say I'm not allowed in there, so I can't go get my model. I won't tell you what I was thinking about doing. And I said, how can I show this model? And so I said, well, let me try doing it virtually. So what I'm going to do is I'm going to take this syringe with blue dye in it, and I'm going to drip it in there and see how it will flow. So there goes the drop. It goes into the Moraine. Now it goes down, it goes down. Now, when it reaches this point, which direction is it going to flow? Well, you can see that the arrows there are telling it's going to move in this direction. And that makes sense because it's going to flow to the what they call potentiometric surface. It's going to flow to where the hydraulic head is the lower. And so when it comes to this, it travels, and you can now see what is the water doing? It's traveling uphill. So people always ask, how can a stream move uphill? Well, it's moving uphill, travels uphill, and then finally it just escapes. And then it's going to be picking up a lot of sediment as it's traveling through here, and it's going to just dump the sediment out onto the outwash plain then. All right, so let's see what a tunnel looks like. Here, the Black Rapids subglacial tunnel in Alaska. Now, if you look at it, you can see the scalloping even on the roof. And it's thought that that scalloping is due to turbid water, water that's in turbidity flow. That means that it's not a laminar flow, it's actually flowing very turbid with the many eddies in it, I guess the best way of saying it. Lots of eddies in it. And that's forming these scallops here. And you can see now, that's a pretty big valley or tunnel. And then underneath here, you can see this is the sediment. The level of the sediment was up here, so it's probably taken out all that sediment, maybe more, and then maybe left some after it stopped. So it's a beautiful thing. So characteristics of tunnel valleys. They're anastomosing. These are, once they come out, they're anastomosing, or underneath the glacier, they're anastomosing. That means they have this pattern, similar to the braided streams. They may go uphill and downhill. Since you can see that they're under high hydraulic pressure, they don't care about up and down very much. And they may terminate in outwash fans at ice marginal positions. And now here we can look, we have lots of tunnel valleys. If you're going on 25A from Stony Brook, here's 25A comes here, takes a right, you're traveling up through here, you're traveling in a tunnel valley. And the railroad station is probably right in here. And then when here you're going up, you're now reaching top, and then here you're going back down again until you reach here. This is so there's an uphill and downhill. Here's a case now of sheep pasture. If you're on sheep pasture road, you're traveling along through in a tunnel valley. And then at some point, the tunnel just left the surface and went up into the glacier. And you can see another tunnel that was here before did exactly the same thing. So they can just terminate whatever they feel like. So now you can see here now, this is the 25A tunnel valley coming like that. And here's the sheep pasture tunnel valley going like that. And then I just want you to think now when you're going up 25A there. You're all familiar with this, I'm sure. Here's the main street into Stony Brook. Here's 25A coming out. And I'm not exactly sure where my picture is, but I think it's about right here. And I want you to think about it when you're driving again up 25A. So it's nice to think about the geology when you're traveling around. And you can see now that definitely a valley wall here, right? And very definitely a valley wall here. And this is the floor of the valley. And you're traveling along here and you're going uphill all the way. And you can just picture that the water was traveling in this tunnel valley along the floor here. And sometimes probably not much fat. Probably sometimes when, if you've been on 25A and it's packed, they would be traveling faster than the traffic is flowing. So you can see it's a beautiful case. And whenever you're traveling around in the North Shore and you're seeing a situation like this, you look, is there a tunnel valley? Is there a wall to my left, a wall to my right? Am I traveling up or down a gradient? you might just say, oh, I'm in a tunnel valley. So let's talk about the development of Port Jefferson Tunnel Valley and outwash fan. Here is Port Jefferson. This is the harbor. And then this is the Interglacial Moraine. Here's Stony Brook Moraine. And here you can see is the Port Jefferson fan. And let's just consider then what could be happening in this situation. Here is the trench. So this could be a trench. Now, at that time, when the glacier was over it, this trench was deep. And it could very well be that some of that water can actually accumulate in this trench and be in a subglacial lake. That's one of the hypotheses here. And it would be a huge lake. And then as melting's going on in the summer, the lake starts getting full, and then the system becomes unstable, and the lake water has to get out of there. And so here we can see a close-up of it. Here is Port Jefferson Harbor, and here is the trench. It's pretty big. Now this is just the bottom of the trench. It's not the whole size. This is just the bottoms where it's intersecting the basement rock. So it's much larger than this in width. So it's a huge, huge thing. This has been picked up because it just shows the basement rocks at the bottom of the trench. So now let's just see what's happening. As the glacier retreated after forming the Ronkonkoma moraine, there was a proglacial lake in front of the glacier. And then the glacier starts re-advancing. As it re-advances, it forms in the Stony Brook Moraine, and here's an interlobate position here. And then this is called the Roanoke Point Moraine, and you can see it's got much lower relief on it. This is the Stony Brook Moraine, and you can see now we have all these tunnels here feeding sediment out onto the outwash plain. And here we can see the glacial tectonic features of the Stony Brook Moraine. And now this is not a good picture, but I have to redraw this. But this could be the subglacial lake that's out further out into the sound, what's presently the sound, and the lake can become unstable because it's just filling up with too much water, and it's going to try to find a way out. Now, what's proposed is that this is an interlobate moraine. That's an area is a weak spot. So that's probably a good spot for the water to sneak out. And then it does do that. And it forms then the outwash plain here. And it comes out in probably many different, maybe more than one events, maybe annually, every summer when you got more water. And then this is a trip now up 25A, up Main Street, if you like, going through Port Jefferson. And so right now you can see we got a valley wall here, and we're going to just travel up it, and you can just see now. And here's a boulder that sits in the parking lot here. Dated, it's about 18,000 years old. That's been sitting there, and now you can see it's getting steeper and steeper as we're moving. It's steeper, and then we're going up to sheep pasture. You get to sheep pasture and it flattens out, but it's still going up. And now we're starting to approach. It's flatter here. And then once we get to the railroad track, we can look out here and see it's going down. The gradient is toward the south. It's going here. So our hypothesis would be that the glacier front was sitting somewhere right in here. Just sitting right in here, and the water was just pouring out here and dumping all this sediment out to the south. And then on a field trip, if we were on a field trip, I usually go and park somewhere in here, and then we stand out here and look into it. And we can do that today also. Here we are, we're standing there, except now we're standing in the street. Here's the railroad track. The glacier is right here. And there's a big tunnel right here. And I always tell students, you gotta imagine what it is. And so this is, I'm gonna imagine it for you. So look at that, see, there it is. There is the tunnel, and there's the glacier, and there's the front of the glacier, and there it is in my imagination. You can just see now. Next time you go there, as you approach the railroad track, just think, huh, there used to be a tunnel here. It was pouring out water. You could just imagine the huge quantities of water that was coming out of there. And then during the winter, you could probably go in there, and if you had a good car, you could probably go drive down into it. And you see this beautiful scalloped tunnel walls. Questions or comments?
Okay, so we had a few in here. The Little Ice Age is said to have ended about 1850, sort of corresponding to the Industrial Revolution. Coincidence?
Most people think it's a coincidence, not only a coincidence, but maybe related, because the CO2 started increasing then.
Then Robert asks, did the trench predate the glacier, or was a result of the glacier?
It's thought to be a result of the glacier. It's thought to be a result of the pushing of the glacier and pushing all those sediments up into the moraine. You got these moraines, you have to ask, where did they come from? We know we can see the sheets in the moraines, and one of the first questions we had is, how do we get all these big sheets? We don't see any place they came from. Well, once we realized there was a trench out there, we said, ah, there it is. That's the source. You have to have a source for the sediments, and there is one.
Laura says, awesome, it was much more beautiful then. And Laurel has a question.
In the picture of the tunnel in Alaska, you have a man standing there. How much ice was above him? How many feet or?
I don't know that. I don't know that. He's probably near the front of the glacier, so it's probably not very thick there.
Oh, okay.
Any other questions? If you want to raise your virtual hand. Nothing else in the chat that I can see.
Okay.
That's all the questions.
All right. Now we'll go on to climate. Each year's snowfall is stacked up and preserved atop glaciers, forming layers almost like annual tree rings as seen here. And so you can actually see the tree rings, right? And the reason that happens is that during the summer or during the winter, you get the snowfall, and then during the summer, you get some melting. And then sometimes you even get more dust and stuff that comes out on it. So you can even have dark layers, but you can see get a melt layer and then a ice layer. So just complete continuation of this. And so if you're in a place like the glacier in Greenland, there probably wasn't a melting that would completely eliminate the previous year's winter ice. So therefore, as like tree rings, you can actually just count the years. And this is an incredible way of doing the dating. And you can do this in Greenland. They have machines. They put their ice cores in the machine, and they can actually count. They just put it in there, and the machine will count the years. It's got some uncertainties, but they think that you can do it within years. And here is a chunk of a core of a Greenland ice. So they dug it, they pulled it out, and the Greenland ice or any glacier ice has bubbles, because you realize that when the snow falls, it's 90% air. Is that right? Just when you look at the bottom. Then as the snow gets covered and collapses, the air gets pushed out. But even at the time when you have glacial ice, you're going to have still some air left in it. And you can just melt the ice and take the air out and analyze it. And you can actually look at what was the air like in the past. And you can do it with you can't do it for every with a 1-year resolution because the air has been moving up and down through the snow as it's been melting or is collapsing. But you can get it probably pretty close to a few years, maybe 10 years. You can do it. And so now what they can do is they, in this case, they can measure the temperature by using oxygen isotopes. And this is the temperature in Greenland in degrees Celsius. And this is the age in thousands of years before present. And this is the amount of snow that accumulates per year. And so this is going 20,000 years ago. It's called the last glacier maximum. That's when the glaciers probably left Long Island 20,000 years ago. And you can now see the temperatures. And so in this case, the average temperature there was minus 45 degrees Celsius. That's minus 50 degrees Fahrenheit. And then it stayed pretty cold. Even got colder at times until about 15,000 years ago. Then it warmed up. Then we had cold and warm periods a couple times. But then in the younger dryas, we had a really, really cold period. And in the Greenland, it looks like it went down to temperatures similar to what we had at the last glacial maximum. And then it stayed down there from 12,900 to 11,500, and then warmed up very rapidly. This happened very fast. They see that this is as fast as they actually can measure it. And it's the same thing, it warmed very fast. So something happened during the younger dryas, and it warmed up really fast, and then warmed up, and then we went into our period right now, which is the period that we're the interglacial period. And here's our temperature right now, and you can actually see in the past it was warmer, and there's some hint in that in here. But we're interested now what's happening in this part. And again, you can see snow accumulation is low when it's cold, increases when it's warm, decreases again when it's cold, and accumulates even more when it's warm. So cold does not mean you get more snow. It actually means that you quite often get less. So the glacier just left. What was the weather like 20,000 years ago on Long Island? The mean annual temperature was 15 degrees Fahrenheit. That means half the time the temperature was above 15 degrees and half the time it was below 15 degrees. Now you probably have been paying attention to temperature on Long Island, and you realize that about half the time, or you'll realize that very seldom we get temperatures less than 15 degrees. Much less say half of the time it was below 15 degrees. So it was really cold. So the ground was permanently frozen, except in summer when the upper few feet thawed. It's a desert tundra. And here's what it would have looked like, something like this. Not much vegetation, a lot of bare spots. And in the winter, now we can see their mammoths. I don't know if they've been there. They were traveling around in this area. And of course, saber-toothed tigers, cats, were looking at the baby mammoths for something to eat. And then muskox that were eating the shrub willow in the area. Then about 15,000 years ago, it began to warm. So we had spruce forest on permafrost. So it would have probably looked something like this. This is permafrost, spruce forest on permafrost in Alaska. Our terrain would have looked something like that. It was green. And then now the mastodons came. The mastodons came because they're browsers. And so they will come when there's something to browse. And the mammoths are grazers. So they like to be in an area where there are grasses and sedges and small shrubs. So you can see the reason we're finding mostly mastodons now in New York, they find quite a few of them, is that during the period 15,000 years ago, there was probably a lot of places where it was warm enough so that there were bogs, and the mastodons would get stuck in them and then die in them. We don't find many mammoths, probably because there wasn't any place for them to be stuck. So 12,900 years ago, the Dryas octopetala appears. That's why it's called the Younger Dryas. Dryas octopetala is a flower that grows under the coldest conditions. And when they were looking in Europe, they noticed that they had Dryas octopetala till about 15,000 years ago, and then about 12,900 years ago, in bog cores, they found Dryas octopetala flowers appear. So the climate became very cold. Clovis culture disappeared. We don't talk too much about it, but the Clovis Indians were in the area, all over this area, all over North America, actually, starting about at least 14,000 years ago. And they disappeared about 12,900 years ago. And this is a big one. The megafauna went extinct roughly about that time. And so there's a lot of concern as to why they went extinct. Were they killed off by the Clovis culture that just came in? Was it the cold climate that killed them? Or were there some other events that might have killed the megafauna? And the megafauna, there were just huge numbers of camels, horses, types of horses, camels, different bison, big bears, wolves, different kinds of wolves, and of course the mammoths and the mastodons, the saber-toothed cats, a whole bunch of these big animals that were just killed off at that time. And then dust-like sediments were deposited on Long Island. I'm not going to talk about that. I've talked about this a number of times. If people would be interested, I could talk about that at a later time, because they have something to do probably with what's happening at the time. And this is Dryas octopetala. It's a beautiful little flower, right? They're really tiny, and they like to be out in the cold, cold weather. And so there, again, now what happens is that we were cold, stayed cold. Some people like to tell you that the reason that the glacier retreated is it got warm. No, it didn't get warm. It was retreating while it was really cold, and probably because even though it was cold, there wasn't much snow falling, and it melted during the summer. And then during this period, we find that the temperature rose, and then it fell very rapidly during the Younger Dryas, warmed up, and then we're here in our period. So 11,500 years ago, the Younger Dryas ended. Climate warmed rapidly. End of the last glacial period, which is called the Wisconsinan, and we then began the present interglacial period, the Holocene. So here's a history then. Glaciers during the last glacial maximum reached Long Island about, say, 25,000 years ago. We're here till about 20,000 years ago. Most of the surface features of Long Island were created between 25 and today, but mostly during that period, between 25 and 20,000. Hummocky terrain, push moraines, outwash plains, tunnel valleys. I think we've discussed all of those. And the climate has changed from a desert tundra to temperate forest that we have today. Return to near glacial period temperatures between 12,900 and 11,500 from the Younger Dryas. And time for questions and comments if you have any. I've covered a lot of material and fast. I hope some of it is stickable.
Okay, so C. Barnes asks, so is the North Shore wasn't only from Connecticut?
I'm sorry?
Yeah, I'm not clear on what he was asking, but it says, so the North Shore wasn't only from Connecticut. Let me see if I can unmute. C. Barnes, can you unmute yourself? Let's see. Yeah, I don't know that he can, or she. Well, they're not unmuting themselves.
Okay.
Let's see, ask to unmute. Let me see if I can unmute them. No, they have to unmute themselves. Any other questions? I think Abe Trenk You have your hand up. Unmute yourself.
Oh, here we go.
Yeah.
Okay. I think something similar on the big island of Hawaii. I remember walking through a tunnel where there had been lava flows. And it wasn't as impressive as the picture and the one in Alaska, but it was a little spooky. It was right near where there are still lava flows still on the big island.
Right. Valleys or tunnels in the lava flows are rather common. And in fact, they're one of the things they're thinking about, since there are big flows in Mars and on the moon, maybe they could actually use a place to go to stay inside of them if they wanted to inhabit the areas.
Interesting. Okay, Laurel, you have a question? You have to unmute yourself.
I think what C. Barnes was asking, because I was wondering about it also, is that all the rubble and the boulders and everything, was it all coming from Connecticut onto Long Island? Was, you know, when the glacier was coming down from the north, did it push a lot of Connecticut into Long Island?
Boulders can't travel more than about 20 miles at the base of a glacier. And so most of the boulders that we find on Long Island are probably from the trench, from the basement of the trench. And because the rocks in Connecticut have a different composition than the boulders that we find on Long Island. And since the boulders can't travel very far, the most likely place they came from is the trench that was just offshore.
Oh, okay.
So he did ask or he or she, I can't tell. I was always told that the North Shore was pushed down from Connecticut, but it sounds like it is from the bottom of Long Island Sound.
Most of it is, yes. But it would be, there's always going to be some from Connecticut and so forth. But most of the sediments that would be available would be in the Sound area.
Let's see. Okay, it says, I'm sad to say this was my first lecture with Dr. Hanson. Will he teach an OLLI class in geology going forward? If we can convince him to. Here's another question. What was the main factor of how Long Island Sound was formed? Was it a lake under the ice?
The trench was probably a lake under the ice, but the Long Island Sound is actually a position where the bedrock of, I don't know if you people can see me. If this is the bedrock of Connecticut, can you see that? Here's
Well, if you stop sharing, Dr. Hanson, are you finished with your presentation?
Stop sharing, yes.
Yeah, then they can see you in a bigger screen.
Okay. Yeah. So then, if you picture this is the bedrock of Connecticut, and then what happens is that on top of the bedrock, you're having sediments that are being deposited on it. And Long Island Sound is exactly.
Excuse me, your hands are a little too low. Thank you.
And so this is the basement rocks of Connecticut coming to the south, and these are the sediments that were piling up on it. And you're going to see the Long Island Sound is exactly those two types of rock intersect. So this is going to be the basement, and this is the sediments, and you can see that that is exactly where the sound is. So it is an intersection of the two different types of sediment. That's how it's formed.
There's another question here from Laura. What about Lake Ronkonkoma? Is that a big kettle hole?
It's thought to be. It's got all the characteristics.
I think that's it for now. That's all I have in the chat. Any other questions? If you want to virtually raise your hand before we conclude. Any other questions? No, I think that's it. So we thank you, Dr. Hanson, very much. This was very informative.
Well, thank you. I'm glad you gave me the opportunity to present some of these ideas.
This was wonderful.
Some of the ideas I'm presenting are you may think are new, but the glacial tectonics was well known over 100 years ago, but has never made it into the public understanding of the area.
Well, I thank you. I'm letting everyone unmute themselves if they'd like, but we're getting a show of hands here, clapping because
Okay.
I enjoyed the lecture. So thank you so much. This was really
You're welcome. Thank you.
Thank you.
Thank you. William, have you written any books?
Have you written any books?
Oh.
Is that? Dr. Hanson, have you written any books?
Lots of papers, not books.
Okay.
Worked on the web that I've worked with the students on. And if you do searches, you can find them fairly easily. Almost everything's on the web.
Okay. Anybody else? Any other questions? All right. Well, thank you, Dr. Hanson.